Okay, let's do section 1.3, trigonometric functions. And this is really just a super quick review of the material of Pre-Calculus 2, trigonometry. I have online notes posted. If you'll click on the link there in the PDF file, it's posted online of this material. That'll take you to some Pre-Calculus 2 notes. Probably a good idea to refresh your memory on all the trig functions and their graphs and so forth. So that's the plan in this section. It's a good deal of material. We're leaving out a lot of details too and taking some things as given. We're going to measure angles in radians, not in degrees. Reasons to be revealed later. We have to measure angles in degrees. I'm sorry, in radians, in calculus. Some of the manipulations we'll do only hold if you measure angles in terms of radians. So degrees won't do. If we're given angles in terms of degrees, we'll probably convert them to radians. Here's the formal definition of the radian measure of an angle. The number of radians in the central angle, A prime, C, B prime in this picture, A prime, C, B prime. So we got a circle, and this blue sector here indicates what the angle, we'll call theta, and measure in terms of radians, what the angle theta is. So central angle, that means its vertex is at the center of this circle. We're taking a circle of radius r, there's parameter r, so circle of radius r. The number of radians in that angle is defined as the number of radius units contained in the arc S subtended by the central angle theta. With central angle theta measured as theta radians, this means, it's probably this I want to look at, S equals r times theta. They said S was the S subtended, it's the radius units contained in S. It's how many copies of the radius r there are along this arc S. So we get S equals r times theta is the relationship for arc length and theta. This comes from the very definition of how we're measuring theta. If I want to take this and solve it for theta, then we get theta equals S divided by r. So the radian measure of this angle is this arc length, the arc length of this sector, S, the piece of crust on the pie, if you will, divided by the radius. We'll measure distances in terms of whatever units, and we'll have S units divided by R units. Notice then that theta is unitless. S is a measure of length, R is a measure of length. You take the quotient, and I don't know if you're measuring lengths in centimeters, the centimeters will cancel, and you'll be left with theta as a unitless measure of angles. We can convert from degrees to radians, which we'll want to do on occasion. We could convert from radians to degrees, which I doubt we'll be terribly interested in that, but an observation of how to interchange degrees and radians. They will give us degrees sometimes, and we'll probably have to change them to radians. We will if we're doing calculus stuff. In this section, we're reviewing, so I don't particularly need radians, but I want to review it because that's what we'll use when we deal with the calculus stuff and trig functions. One complete revolution of the unit circle is 360 degrees. So 360 degrees in a circle. The circumference of a circle is 2 pi times the radius. We said unit circle, so the radius would be 2 pi times 1. So we get 360 degrees corresponding to 2 pi radians. I could say 360 degrees equals 2 pi radians. Divide the 2 out to the factor of 2. We'd get pi radians equals 180 degrees, half each of these. So let's take this equality and let's divide both sides by pi. That'll leave us with 1 radian on the left. It'll leave us with 180 divided by pi degrees on the right. So 1 radian equals 180 degrees divided by pi. That's approximately 57 degrees. So FYI, a radian is about 57 degrees, just to give you some attempt at visualizing what a radian is. Not terribly important. This 57.3 degrees. We'll do computations precisely most of the time, as you would even if you wanted to approximate. We'll do the approximations at the end if we approximate. We could also take this relationship, pi radians equals 180 degrees, and divide both sides by 180. That'd leave us with 1 degree on the right-hand side, and it'd leave us with pi divided by 180 on the left-hand side. So we get 1 degree equals pi over 180. For the record, that's roughly 0.017. And if I keep up with units, then I'd say 0.017 radians. But radians are a unitless measure of angles. So we may write radians out sometimes to emphasize we're dealing with angles and not something else. Or we may not. So I'll maybe write radians. I don't have to. And the only reason I would was to emphasize that we're actually dealing with angles and some of this stuff. So degrees are not unitless. So if I measure angles in degrees, I got to use the little degree symbol. I measure angles in radians. I don't need a symbol for radians. They're a unitless measure of angle, as you can see from the way we defined it in the previous definition. All right, so the emphasis will be on radian measures of angles. In Calculus 1, if we're doing calculus things, we must use radians. We'll do some techniques, differentiation, and the statements we'll make, they won't be true unless we measure angles in radians. And I can always convert back and forth if it really bugs you. But the calculus stuff must be done in terms of radians. When you've encountered radians before, it was probably highly unmotivated. The benefit of radians is, the benefit of radians is it makes it easy to measure the length of the crust along the pi. It makes it easy to measure arc lengths around a circle if you measure central angles in terms of radians instead of degrees. So there's your past experience as to making radians something natural, an artificial argument, one might say. But in here, we're stuck with radians. We can't get around radians. We're stuck with radians. Unavoidable. Let's look at exercise 1.3.2. So let's go to the supplements for this section. And they give us a central angle in a circle. A central angle in a circle of radius 8, r equals 8, in the symbols we just had, is subtended by an arc length 10 pi. S equals 10 pi in terms of the symbols we just had. Find the angles, radian, and degree measure. Okay, so they want us to find theta in terms of radians, and then we'll convert it to degrees. All right, so they gave us a circle of radius r equals 8, something, centimeters maybe, and an arc length s of 10 pi. They didn't give us units for these. If they did, presumably the units would be the same. We'd have, say, 8 centimeters and 10 pi centimeters. We're going to express theta as s divided by r. So we'd have centimeters in the numerator and centimeters in the denominator, and units cancel just like numbers do. So we'd end up with a unitless theta. We're expressing theta in terms of radians. So we'll get theta equals s over r. Here, s is 10 pi, r is 8. 2 goes into 10 5 times, and 2 goes into 8 4 times. So we can simplify that to 5 pi over 4 if you want to simplify. Yeah, I guess I want to simplify because we're going to do something else to it. Do not approximate it, though. This is a math class. There's the precise value. You want to pick up a calculator and express that in some decimal thing? I say in here, why bother? This is the exact value. The calculator won't give you the exact value. It'll give you an approximation. Technically, it gives you the wrong answer. We got the right answer. We've got the precise answer. Keep it. You want to approximate things? I say don't bother in a math class. You take a physics class and you want to measure things to certain numbers of significant digits. I mean, you're still probably going to have to do the precise computation, and then you do the approximations, plugging in values to certain numbers of significant digits in physics or in engineering. So it's easier in math. You take the exact values and you stop with the exact value. No need approximating. There's the radian measure of theta. Theta equals 5 pi over 4. They want us to convert it into degrees. Better use that degree symbol in this case. Okay, we had conversion factors, As we saw, 180 degrees over pi equals 1 radian. That's what we had. So we'll take theta, 5 pi over 4, times the conversion factor, 180 degrees, divided by pi. Now, if you like to keep up with units, including the radians, we've got 5 pi over 4 radians. And here we've got 180 degrees divided by pi radians, if you like. Well, the radians will end up canceling anyhow. Radians are a unitless measure of angle. And we do the arithmetic, and this simplifies to 225 degrees. And no need to approximate. They actually gave us some nice angles with this. Okay, so there's theta in terms of radians. There it is in terms of degrees. Converting radians to degrees is something we're unlikely to do. They give us degrees. We're going to probably go the other way and convert degrees into radians. But we've got a conversion factor for that as well. Back to the notes. Angles in standard position. An angle in the XY plane is in standard position if its vertex is at the origin and its initial ray lies along the positive x-axis. Initial ray, so they indicate these angles with the little arrows. So the initial ray is here. The other piece of the angle is called the terminal ray. So the terminal ray lies here. They say angles measured counterclockwise from the positive axis are assigned positive measures, and angles measured clockwise are assigned negative measures. So positive measure angles will go counterclockwise. You should be used to this from your pre-calculus and high school experience. Angles measured in the clockwise direction are considered negative measure angles. But standard position has vertex at the origin, initial ray of the angle along the positive x-axis, and then the terminal ray lies where it may. The measure of the angle is determined by how much twisting there is, so be careful with that. We will often have angles with the same initial ray and the same terminal ray, but there'll be different angles. There'll be maybe more twisting in one than in the other. And the angle measure is related to, in a sense, how much twisting there is. Technically, it's related to something or other involving arc lengths of circles. But beware, coterminal angles are not equal angles. Equal angles have the same measure. Okay, we're working our way on segueing into trig functions. So we're going to define 6 trig functions for acute angles. Why acute angles? Why these angles even got a name? Acute, because they can be put in a right triangle. So an acute angle is one, if I may, between 0 radians and pi halves radians, between 0 degrees and 90 degrees. If you're still enamored with degrees, that's fine. Need to mature from that a little bit because we're stuck with radians in here. So an acute angle is one I can put in a right triangle. So here's an angle theta in a right triangle. The right triangle is indicated here. We do the standard labeling that in this right triangle for angle theta, this is the side adjacent to theta, this is the side opposite of theta, this is the hypotenuse opposite the right angle. In the right triangle, you know, Pythagoras has got some things to say about the relationships between the lengths of these 3 sides in this right triangle. More of that shortly. But what we're going to do now is define for acute angles 6 trig functions. We'll define the sine of theta to be the opposite over the hypotenuse. Cosine of theta is the adjacent over hypotenuse. Tangent of theta is the opposite over adjacent. Usual ratios of lengths of sides determine these 3 trig functions. We've also got the trig functions cosecant, secant, and cotangent. The relationship and how they're listed here is these 3 are respectively reciprocals of these 3. Cosecant of theta is the hypotenuse over the opposite. Well, that's a reciprocal of sine theta. So we'll get a relationship that 1 over sine theta is cosecant theta. Secant theta is hypotenuse over adjacent. Well, cosine is adjacent over hypotenuse. These are reciprocals of each other. Cotangent of theta is adjacent over opposite. Well, that's a reciprocal of tangent. So each of these three is a reciprocal of these three respectively. And you've dealt with relationships between trig functions before. We got a little problem with what we just did. That was only good for acute angles, and we need the trig functions to be defined for any angle, not just an acute angle. So we're going to define the 6 trig functions for any angle, not just an acute angle. You might want to read parenthetically there. By first placing the angle in standard position in a circle of radius r. Radius r. You're used to probably doing this with the unit circle where r equals 1. Well, we can plug in r equals 1 and we'll get your way of doing it. Then we'll define the trig functions in terms of the coordinates of point P, where the angle's terminal ray, here's the initial ray along the positive x-axis, here's the terminal ray for this angle theta. The point P is the point where the angle's terminal ray intersects the circle. Terminal ray, circle, they intersect at that point right there. So, for a given angle, make it a little bit bigger since we read that verbiage up there. For a given angle in standard position, we'll find a point on the terminal side that lies on the circle of radius r. I'll agree with you, r equals 1 would be more convenient. We'll standardize things like that sooner or later. We're defining the sine of theta to be y over r. Y is the y component of this point on the terminal side. R is the radius of the circle. Cosine of theta is x over r. X is the first coordinate of this point on the terminal side. R is the radius of the circle, and so forth. Secant is r over x. Cosecant is r over y. Tangent is y over x. Cotangent is x over y. You know what x, y, and r are from the coordinates of the point in the radius of the circle. These 6 definitions consistent with the previous 6 definitions. If we were to draw an acute angle, then we'd have that angle in standard position. It would be a first quadrant angle. We could draw a right triangle containing that angle, and off you go. Funny thing, you see in this picture, you see a right triangle that contains angle theta. You do not. I see a little right triangle here. Here's its hypotenuse. Here's one side, and there's the other side. So there's a little right triangle. That doesn't contain angle theta. Angle theta is too big to be in a right triangle. It's not an acute angle. It's an obtuse angle in this picture. So yeah, well, there's a right triangle involved in the conversation, but it's not a right triangle that contains theta. Theta's too big to be in a right triangle. All right, well, that's why we drug all this x, y, and r stuff into the conversation. And now we have the trig functions defined for any angle. Well, let me take some of that back. I can't divide by 0. Okay, let's see, the radius of the circle, we wouldn't have a circle of radius 0. So sine and cosine, we're good. Secant has an x in the denominator, and so does tangent. There are points on this circle that have an x coordinate of 0. These trig functions won't be defined for the corresponding angles. We've got y in the denominator of these two, okay? Then these two, cosecant and cotangent, will not be defined for certain angles. Those which have a point on the circle of radius r where the y coordinate is 0. Let's see, that happens at this point, for example, and this point over here. We'd have a x coordinate of, here we've got looking at r comma 0, x, y. Here we're looking at negative r comma 0, x, y coordinates. So sine and cosine are defined for all angles. Secant, cosecant, tangent, cotangent are, let's just leave it at this for now. They're not defined for all angles. There's some bad angles. And the problem is division by 0 in our definition of those. So can't be done. We've mentioned that. By the definition, we immediately have the trig identities. Tangent theta is sine theta over cosine theta. Secant theta is 1 over cosine theta. Cotangent theta is 1 over tangent theta. Cosecant is 1 over sine theta. These reciprocal relationships I pointed out in the acute setting. Same thing holds here. Let's see, let's look at the tangent, cotangent one, these two. I take the reciprocal of one of these, y over x, I get the other one, x over y. So these are reciprocals of each other. Cosecant is r over y. What's that? The reciprocal of sine, like we had before. They're lined up differently in this little presentation. And let's see, x over r and r over x. Cosine and secant are reciprocals of each other. Oh, we said tangent is sine over cosine. Hopefully an identity rattling around in your head from your past experience. If I were to take sine theta and divide it by cosine theta, we'd have y over r divided by x over r. The 2 over r's would cancel. You'd be left with y over x. We could also express cotangent theta in terms of sines and cosines. So there's a handful of little trig identities there. It's time for talk about special angles. Okay, we'll refer to these as 30, 60, 90 and 45, 45, 90 right triangles. You're used to probably describing them like that because that's the measure of the angles in these triangles, but it's in degrees. So we'll talk about these special angles, 30, 45, and 60, but we need to express them in terms of radians. So I want to be militant about the radians thing early on. It really doesn't matter unless we do calculus stuff, and well, that's why we got together, is to do calculus stuff. So let's take that 30 degrees and write it in terms of radians. It's pi 6 radians. 45 degrees is pi 4. 60 degrees is pi thirds. Easily verified. You have the conversion factor from before. And we have these special triangles with which I hope you are familiar. Here's really a 45, 45, 90 triangle. It's an isosceles triangle. The length of this side and the length of this side are the same. Make that length 1, and then Pythagoras will tell you the hypotenuse has to be the square root of 2. We should have 1 squared plus 1 squared equals the square root of 2 squared. That's 1 plus 1 equals 2. And that checks. So the Pythagorean theorem gives you the ratios of these sides, the lengths of these sides if we set this equal to 1, and then we take ratios. So I may as well standardize it and make one of the sides 1. If I'll take an equilateral triangle, all sides are the same length, all angles are the same measure, that'd be 60 degrees or pi thirds radians. If I take an equilateral triangle and cut it in half, that'll produce this. So that's where that comes from. Being an equilateral triangle, I know that this side will be half the length of what's the hypotenuse in this little right triangle. And now Pythagoras will tell us that the missing side must be the square root of 3. This squared plus this squared equals that squared. 1 plus 3 equals 4. That one checks too. So without going through the details of explaining exactly where these numbers come from, let me appeal to some of your past, or we'll spend all our time in section 1.3. But we get these lengths of sides in these special triangles. So we can find the trig functions for pi 6, pi thirds, and pi fourths. Let's find, how about we do cosine, sine, and tangent, then you can take reciprocals to find the others. Pi 6, here it is. Cosine was adjacent over hypotenuse. This is the adjacent to that angle. This is the hypotenuse. Square root of 3 over 2 is the cosine of pi 6. Sine of pi 6, opposite over hypotenuse, 1 over 2. Tangent, opposite over adjacent, 1 over the square root of 3, 1 over the square root of 3. You bothered by having an irrational number in that denominator? And maybe in your past, there's been an emphasis on rationalizing denominators. Let's not worry with that. So I'm not bothered at all that we have an irrational number in that denominator. Let's leave irrational numbers in the denominator predominantly. It's precise values. There's no need to rationalize denominators unless maybe we're going to add something together. I don't know. So I'm not bothered by the square root of 3 in the denominator there. Most folks aren't when dealing with trig functions. How about pi fourths? Well, here's pi fourths angle, opposite, adjacent, and hypotenuse. Same arguments. We'll get Square root of 2 over 2, square root of 2 over 2, and tangent opposite over adjacent would be 1. Let's see, if we look at, let's look at cosine. It'd be adjacent over hypotenuse. It'd be 1 over the square root of 2. That's not what this is it? Well, it is if you'll rationalize a denominator. Speaking of rationalizing the denominator. You want to write this as 1 over the square root of 2. I'm totally happy with that. It is a bit more common to write the sines and cosines of pi force as square root of 2 over 2 instead of 1 over the square root of 2. When we start manipulating these, I don't care where the square roots fall. I take reciprocals. I might change the form again. Pi thirds, here's pi thirds. There's the opposite, there's the adjacent, there's a hypotenuse, and there's the resulting 3 trig functions. So anywho, you need to have these at hand or in your head, the sines, cosines, and tangents of the special angles, pi 6, pi fourths, pi thirds. That's what they are in size, in increasing size. Pi 6 is smaller, pi fourths is in the middle, and pi thirds is greater. With our definition in terms of points on the terminal side of an angle, and we can go through and find sines and cosines of angles that have a terminal side along one of the axes. Actually, it wouldn't be very hard. We can find sines, cosines, and tangents and the other things as well for angles that are, in a sense, related to these 3 special angles. Let's illustrate that with an example. I thought that was next, where they tell us, okay, this will take a little while. I'm going to streamline it. You have access to the notes to go back and read through the notes or pause the video and read it in more detail. We're going to deal with 5 angles, so there's going to be a bit of redundancy in some of this. It says, finish the following table of trig values for some special angles. So they want all 6 trig functions for -3 pi halves, -pi thirds, -pi 6, pi fourths, we were just looking at pi fourths, and 5 pi 6. This one we could fill in with the information we just had. Pi fourths is a special angle. These aren't special angles, but these other 3 here are related to special angles. Okay, let's look at -3 pi halves. First, -3 pi halves. Okay, we'll have the initial side. We'll go, what pi halves radians is 90 degrees. And we'll go pi halves, another pi halves, and a third pi halves. We'll go in the clockwise direction, so we get a negative angle. So for -3 pi halves, we get this as a terminal side. Let's do this on a unit circle. Do it on any circle of any positive radius that you like. Let's take that radius to be 1. So we're segueing into that now. And then this point up here, we get the coordinates, 0 for the x coordinate, 1 for the y coordinate. So x equals 0, y equals 1, xy equals 0, 1. Now we can go to that definition of the 6 trig functions in terms of x, y's, and r's. We're taking r equals 1 here because we're taking a unit circle. And we can substitute in 0 for x, 1 for y, and 1 for r. And that produces the following. Sine is y over r, 1 over 1 is 1. Cosine, x over r, 0 over 1 is 0. How about secant? Secant was r over x. X is 0, so we can't do that one. That one's undefined. And so forth. For the remainders, we have these defined in terms of x, y, and r. And we know x is 0, y is 1, and r is 1 in this picture. That's good enough to go through and find all 6 trig functions. Ooh, a couple of them aren't defined. X is 0, and secant and tangent involve an x in the denominator. Undefined. Can't do those. Those 2 trig functions are undefined at -3 pi halves. All right, so we'll collect this information together in a table after we've looked at the other angles. Next, they gave us -pi thirds. All right, so here's how we're going to deal with this. Let's go back to that special triangle we had. I think we had a 2 here, a 1 here, and a square root of 3 here. So I've divided the lengths of the edges by 2 to produce a hypotenuse of 1 because we're dealing with a unit circle here. So scale that triangle. I mean, the trig functions are defined as ratios of lengths of sides. So if I scale all the lengths of the sides the same amount, we get the same ratios of the lengths of sides. And let's see, we had, if we had pi thirds here, then we would have, and a hypotenuse of 1, then we would have an opposite side of square root of 3 over 2 and adjacent side of 1/2. I know I'm doing these fast, but this is review stuff. Take that triangle that we saw in the notes. Oh, let's go peek at it again. This triangle, take this triangle, divide each of the lengths of the sides by 2. Why 2? To get a hypotenuse of 1. We'll get a 1/2 here, a square root of 3 over 2 here, and a 2 over 2, a 1 here. So take that triangle, scale it. That'll produce this triangle. I've written it in a different, or drawn it in a different orientation to make it look like it'd fit right in here. All right, so do you see a right triangle? Yeah, definitely. It technically doesn't contain this angle, but if I'll take, if I'll go over a certain amount straight down to the point, that'll give me a right angle there. We'll have a hypotenuse of 1 because we're dealing with a unit circle. Actually, I'd take this thing here, shrink it, and it would set right there, with the pi thirds angle here corresponding to the negative pi thirds angle on that coordinate system. Well, I can use that, and that's the reason I brought this up, to find the coordinates of this point. Because if I can find the coordinates of the point, I can find everything. All right, how far is it over? What's the x coordinate? You go over 1/2. How far down do you go? Square root of 3 over 2, and then the hypotenuse will be 1. Oh, we went down in the x direction, so the x coordinate isn't square root of 3 over 2, it's negative square root of 3 over 2. So I can use the 1/2 and the square root of 3 over 2 in this special triangle to determine the coordinates of the point down here. Just got to be a little careful. We're down here in the 4th quadrant where x is positive and y is negative. So I use the special triangles to find the absolute values of the coordinates. And then I look at the quadrant, and that tells me what's positive and what's negative. Okay, so for theta equals negative pi thirds, we'll find the coordinates of this point are 1/2 negative square root of 3 over 2. So xy, in the notation we had in the definitions, x is 1/2, y is negative square root of 3 over 2. We've chosen a unit circle, so r equals 1. So sine of negative pi over 3, y over r is 1. So that'll leave us with the y coordinate, negative square root of 3 over 2. Cosine is x over r. That'll leave us with the x coordinate of 1/2, and so forth. So we've got x, y, and r. There's x, there's y, and r is 1 because we're taking a unit circle here. There you go. There's the sines and cosines of negative pi over 3. None of them are undefined, right? Neither x nor y nor r was 0. So I don't have a problem with undefined in this one. So what we've got is an angle that has a special reference angle. Reference angle is what you get by going from the terminal side to the nearest piece of the x-axis. The book, I don't think they actually define reference angle. I'd say the reference angle is pi thirds in this one. That's why I go to this triangle with a pi thirds angle in it and reference it to find the coordinates of the point and then find everything. Let's do it again. How about for negative pi 6? Well, it's the same story. Same reference triangle, and I orient it differently. There's a pi thirds angle down here. We're interested in the pi 6 reference angle, if I can use that terminology now. And let's see, we still get that square root of 3 over 2 and 1/2 stuff. That produces, for negative pi 6 angle in standard position, produces an x coordinate, this time an x coordinate of square root of 3 over 2, and a y coordinate of 1/2. No, it's in the 4th quadrant, so it'd be negative 1/2. Let's keep an eye on the plus and minus stuff. But the numbers are the same we get from the triangle, except for maybe they need a negative sign. Depends on which quadrant they're in. Okay, so theta equals negative pi over 6. We get x is square root of 3 over 2. Y is negative 1/2. We're standardizing it, looking at r equals 1, a unit circle, and then I can find all 6 trig functions as we did before. Like I said, let me not belabor the point on this. You have access to the notes to run through and convince yourself I plugged in numbers in correctly. But when I've got x, y, and r, we've got everything. And I get them from special triangles. Let's do another one. Pi fourths, we've already done pi fourths. Well, the technique still works. We'll take the special triangle. Let me convince you this is the correct special triangle to look at by going back to the notes. We had 1, 1, square root of 2. Well, we're going to divide and make the hypotenuse 1, r equals 1. So we'll have 1 over the square root of 2, 1 over the square root of 2, and, well, square root of 2 over 2. We'll have 1 for the hypotenuse. These will be 1 over the square root of 2. If I rationalize the denominator, that becomes square root of 2 over 2. That's where these two numbers came from. So we have rationalized the denominator. It's a standard thing to do in this case. And that allows us to find the coordinates of the point. Hey, we're in the first quadrant, so easy enough. Just square root of 2 over 2, square root of 2 over 2. These distances here, imagine this triangle slid in here. The reference angle actually is this special angle in this case. And x is square root of 2 over 2, so is y, and r is 1 as always. If we deal with a unit circle, if I know x, y, and r, I can find all 6 trig functions. I think we probably did this at least for half of the trig functions in a conversation upstairs. And we're getting the same values out. Let's do another one. Okay, let's do a quadrant 2 angle, 5 pi over 6. Okay, this requires a tiny bit more creativity. This time, the reference angle is the angle between the terminal side and the negative x-axis. Well, we've gone 5 pi 6 of the way over. This would be a total of pi radians. A straight angle, 180 degrees, equals pi radians. So we go from the positive x-axis through pi radians to get to the negative x-axis. We haven't gone a total of pi radians. We've gone 5 pi over 6 radians. Okay, there's another pi 6 radians to get you down to the negative x-axis. So the reference angle, this little angle here, is pi over 6. Imagine taking the triangle and sliding it in there. When we have pi over 6 here, same reference triangle, drawn in a different orientation, got a hypotenuse of 1. We get an opposite of a half and an adjacent of square root of 3 over 6, from which we can determine the x coordinate of that point is related to square root of 3 over 2, and the y coordinate of that point is related to 1/2. So we get square root of 3 over 2, 1/2, plus or minus, adjust for quadrants. We're in quadrant 2, where x is negative and y is positive. So we get negative square root of 3 over 2, 1 and 1/2 for x and y respectively. R equals 1. We've done this several times before. Knowing x and y, we can find everything from those definitions. In summary, there's your table of numbers. Following the book's instructions. We had a couple of them that were undefined, and here's what we get. Let's see, you notice any patterns here? Maybe I should have some sort of reciprocal relationship. Let's look at this column here, the negative pi 6 column. I should have a reciprocal relationship between the first 3 and the second 3. For example, tangent and cotangent should be reciprocals of each other, and they are. Cosine and secant should be reciprocals of each other, and they clearly are. Good thing I didn't rationalize that denominator. Sine and cosecant should be reciprocals of each other, and they are. So I can see some of those reciprocal relationships, by the way, when I look at the table. But there's how you find sines, cosines, and tangents of special angles. Special angles, in general, are angles whose reference angle is pi 6, pi thirds, or pi fourths, because we know those 3 special angles from the little triangles that we drew in the notes. These little triangles right here. So from these triangles, we can find loads and loads and loads and loads of precise trig values. Okay, we want to look at the graphs of trig functions. Told you this is a bunch of material. A function, f, or f of x, is periodic if there's a positive number p such that f of x plus p equals f of x for every value of x. So it's periodic because every p units that the input changes, you get the same thing back out. The smallest value of p is called a period of f, and these trig functions are periodic. They have period 2 pi, or pi, depending on which ones you look at. Claim here is the periods of sine, cosine, secant, and cosecant are each 2 pi. The periods of tangent and cotangent is pi. You've dealt with this before. Granted, we're glossing over some details in this, but like I said, we're doing almost a semester's worth of material in an hour, some odd, however long we talk about this. That gives us a trig identity. Sine of x plus 2 pi is the same as sine of x. Adding 2 pi doesn't change the sine function. It changes the angle changed by 2 pi. It's a different angle, same value though for the sine function. Cosine x plus 2 pi equals cosine x. Similarly for secant and cosecant. Tangent has a period of pi. You add pi to the input, doesn't change the function value. Changes the input, the angles are different, but the tangent values are the same. And similarly for a cotangent function. All right. This gives us, and in a pre-calculus class, we'll probably spend a fair amount of time getting to this stage. This gives us the following graphs of the 6 trig functions. Okay. Cosine function, I can look at the definition. Cosine function starts, cosine of 0 is 1, starts up here at the crest of a wave, and then oscillates like this. It says upstairs the shading indicates a single period. If you can see the shading, if it comes through on the, it's clear in the PDFs of the notes, maybe between the PDF to what I've got here and then the Zoom recording, it doesn't reflect very well. But starts here, contains a single cycle of length 2 pi. So 0 to 2 pi is a single wave of the cosine function. Sine function starts in the center of a wave, goes up, and here's a single period of that. Of course, sine and cosine, as you know from your previous experience, oscillate between -1 and 1. Tangent function looks like this. A single period is given by negative pi halves to pi halves. It has a vertical asymptote on this side and a vertical asymptote on the other side. This thing here, this little piece of the tangent function between negative pi halves and positive pi halves is called a wave of the tangent function. It might seem a little odd to call it a wave. These look like waves here, and that term is used on the tangent function as well, even though it's got these discontinuities in it. So this is called a single wave of this tangent function, and it gets repeated over and over. Just the repetition occurs every pi units instead of every 2 pi units, like for these two. Secant, they say it looks like this. You believe them? Secant should be 1 over cosine, and we have that identity. So when the cosine function's 1, here and here, for example, the secant function should also be 1 here, and they didn't draw it over here at 2 pi, but it should be 1 there as well. Reciprocals, eh? What happens when you take the reciprocal of these little positive numbers? I get big positive numbers. So between 0 and pi halves, we should see the reciprocal, the cosecant function, give out bigger and bigger positive numbers. What happens at pi halves? Well, at pi halves, the cosine function 0, so its reciprocal function's undefined at pi halves. So between 0 and pi halves, whereas the cosine function goes from 1 down to 0, pardon my terminology, its reciprocal, the secant function, will go from 1 up to infinity. There is no to infinity, but that's the standard way to verbalize it. What about over here between 0 and negative pi halves, where the cosine function goes from 1 down to 0? It'd be the symmetric kind of behavior. It'd be the same thing, going in that direction. How about here at pi? At pi, the cosine function takes on the value -1. What's the reciprocal of -1? -1. So it'll take on a value of -1. They haven't labeled the axis as such because it's so cluttered, but we'll get a -1 out here. Now, what happens between, say, pi and 3 pi halves to the cosine function? It goes from -1 through these little negative values to 0. When you take reciprocals of that, you're going to have the secant function take on larger and larger negative values. If you will, it goes from -1 down to -infinity. There is no to -infinity. And similarly in the other pieces. So what we get when we take reciprocals of the cosine function is something that looks like this, where the cosine function is 0, the secant function will have vertical asymptotes. A single wave, and you might object to this word again, a wave of the secant function is this thing combined with that thing. So it's two of these things together, forms a wave of a secant function. What do you think the cosecant function looks like? Well, it's 1 over sine, and sine and cosine, they have the same shapes. They're not the same functions. One is a horizontal translation, a phase shift to the other. Phase shift might be words you used in pre-calculus or in high school trig. But these have the same shapes. And if I take this one and shift it over pi halves units, I get that one. So I expect the cosecant to have the same shape as the secant function, and it does. These are different functions, but they have the same shapes. One is a translation of the other. They've actually taken this picture and translated it to the right pi halves units. And again, two of these things form a wave of a cosecant function. All right, how about the tangent? You take a reciprocal of that, what's going to happen? I take reciprocals of big positive numbers and I get little positive numbers. I take reciprocals of big negative numbers and I get little negative numbers. And what we'll get is a function that looks like this. I was just discussing taking reciprocals of positive numbers between 0 and pi halves. Well, between 0 and pi halves, you'll get then small positive numbers. Take reciprocals of these big negative numbers, we get small negative numbers. And we get something that's a similar shape to the tangent functions. Actually, this function may be turned over. And the cotangent function looks like this. A single wave is one of these things. It looks shape-wise like the tangent function. Tangent function's always increasing, cotangent function's always decreasing. So there's that. So there's some differences as well. Oh, and wherever the tangent function is 0, the cotangent function has a vertical asymptote. Yeah, well, take that tangent. Wherever the cotangent function is 0, like at pi halves, the tangent function has a vertical asymptote. So where one is 0, the other has a vertical asymptote. And there's sort of a dual relationship between these two that we didn't have between, say, sine and cosecant. When this one has no vertical asymptotes, for example. Sine and cosine were always between 1 and -1. Secant and cosecant are never between 1 and -1. Well, they do take on the extreme values 1 and -1, but they never take on other values strictly between -1 and 1. So there's the graphs of the 6 trig functions. We'll probably recall those now and again. Are you good at graphing trig functions? Actually, probably so. You figure out amplitudes and periods and phase shifts and things like that. You're pretty good at graphing, certainly sines, cosines, and tangents. And if you can graph those, you can graph these reciprocal functions as well. I start combining trig functions with other things, then maybe you're not so good at graphing those. Well, calculus will help. There's symmetries in those graphs up there. Let's point to the sine and the cosine one at least. This cosine function is symmetric with respect to the y-axis. That means it's an even function. We discussed even functions in section 1.1. So cosine function is an even function because it's got the kind of symmetry that even functions have. Sine function, this one has symmetry with respect to the origin. If I go over and up and find a point on the curve, if I'll go back and down the same distances, I find another point on the curve. If I go how far over do I go? Way over and up, go way back and down, and you'll find corresponding points. We had pictures of what this kind of symmetry with respect to the origin is, and odd functions have that kind of symmetry. This function has that kind of symmetry. This is an odd function. So even function, odd function. By the way, this is an odd function as well. Tangent function is an odd function. This one is symmetric with respect to the y-axis, so secant must be an even function. Cosecant is an odd function. In summary, without getting too much into that, here's a list of which is even and which is odd. Cosine and secant are even. Sine, tangent, cosecant, and cotangent are odd. You think it'd be 3 and 3, but it's not. 2 of them are even and 4 of them are odd, and there's reasons for that. We can express this evenness and oddness in terms of how they treat negative x. Sometimes they absorb the negative x. Secant of negative x is the same as secant of x. It absorbs a negative just like a cosine does. Sine function, perpetuity, spits out a negative sign. You feed it a negative x, it spits the negative out, as does tangent and cosecant and cotangent. A theorem, quote unquote theorem maybe, cosine squared plus sine squared equals 1 for every theta. All right, that's basically it's the Pythagorean theorem. Let's not go through a formal proof, but let's draw a picture at least. You draw any angle theta, positive, negative, acute, obtuse, gigantic, or tiny. Find a terminal side of that angle and a point on the unit circle where that terminal side intersects the circle, and you can draw a right triangle. It'd be a right triangle. Here's the hypotenuse, which will be length 1. This distance here will be the absolute value of the cosine of that angle. This distance here will be the absolute value of the sine of that angle. And after all, the coordinates of this point, the x coordinate would be the cosine, and the y coordinate would be the sine. Didn't we say that? Actually, we said x over r and y over r, but we've taken r to be 1 this time, another advantage of the unit circle. And the coordinates of this point will be cosine theta, sine theta. So when I measure distances, I have to put absolute values on there because distances are never negative, and well, sines and cosines could be negative. Coordinates of points could be negative. One of these is negative because we're in the second quadrant. The x coordinate, the cosine of theta is negative for this angle because we're in the second quadrant. So anyhow, if I put absolute values on there, I can draw this little blue right triangle. By the way, what's the hypotenuse? Unit circle, the hypotenuse is 1. And then we'll get the relationship. Hey, x is, well, it's plus or minus cosine theta. Y is plus or minus sine theta. The Pythagorean theorem would tell us this squared plus that squared equals 1, which is what we have up here. We lose the absolute values, but hey, we're squaring things, so we're okay. Also, I could take the x coordinate and plug it into this formula, and the y coordinate and plug it into this formula and get it a different way. So no matter how you slice it, cosine squared plus sine squared equals 1. That actually is the Pythagorean theorem in the lingo of trigonometry. From that identity, let me shrink it a little bit so I can see these all at once. From the, shrink it a lot, from the Pythagorean theorem, cosine squared plus sine squared equals 1, we could divide through by cosine squared. Divide both sides by cosine squared, or divide both sides by sine squared. And that would produce, at the bottom of the slide, these other identities. 1 plus tangent squared equals secant squared, and 1 plus cotangent squared equals cosecant squared. We'll use these identities a little bit. In calculus 2, you'll use these identities a bit more. So these are important identities. They are just really special cases of the Pythagorean theorem, written in terms of different trig functions. But you can divide sine squared plus cosine squared equals 1 by the appropriate thing and produce these two equations. Okay, without justification, or maybe with a reference, we get the following summation formulas. I refer you to my pre-calculus 2 notes on sum and difference formulas to get the following. The cosine of angle A plus or minus angle B, so I'm really stating 2 equations at once, is cosine of A, cosine of B minus or plus sine A. sine B. The plus on this side corresponding to the minus on that side, and the minus on this side corresponding to the plus on that side. So plus or minus, minus or plus, respectively. Summation formula for cosine, you've seen this before in your many travels. There's also a summation formula for sine, as given here. Sine of, sorry for the end of line there, sine of A plus or minus B is sine A cosine B plus or minus, correspondingly, cosine A sine B. And I can use those to find a summation formula for tangent. Tangent is sine over cosine, so I could take a quotient of the appropriate stuff and modify it. And we would get the tangent of A plus or minus B is this thing in terms of tangents of A and B. So proofs of those are given in using a pre-calculus class. Click there in the PDF and that'll take you to the links for those. They're proved using some triangles. They're proved using triangles and identities with triangles. Double angle formulas. Cosine of 2 theta is cosine squared theta minus sine squared theta. Easy enough, just plug theta in for both A and B, and that will produce this. Sine 2 theta, 2 sine theta, cosine theta, plug A equals theta plus B equals theta, and that will produce this formula. Tangent of 2 theta, let A and B be theta and add, and that will give you that formula. So that's how you justify the double angle formulas. Piece of cake. Once you've got the summation formulas. Half angle formulas are a touch more subtle. See section 6.5 from my pre-calculus 2 notes for the half angle formulas. They're called half angle formulas when they're written in this form because here we've got 2 theta and here we've got half that, and that's the case in the other two as well. So you might see it written with a theta over 2 where I've got the theta and a theta on the right-hand side where I've got a 2 theta. But these are the half angle formulas. Deriving these is, it's related to the summation formulas, but a little bit more involved. You gonna remember all these? Awesome, I'm impressed if you can. When we need them, we'll look them up or refer to them. More likely than not, I don't expect you to carry all this stuff in your head. We'll use them, but we won't use them so often that we'll be forced to remember them. Let's illustrate one of them in exercise 1.3.31. Use the addition formula, the summation formula, to derive the identity cosine x minus pi halves equals sine x. Okay, we got a cosine of a difference. The addition formula, the a minus b part of the summation formula, has told us cosine a minus b is cosine A cosine B plus sine A sine B. It's just what we stated a few seconds ago. So we'll take, in that cosine function, we'll take A to be x and B to be pi halves. We'll substitute in, and that produces cosine of x minus pi halves is cosine A, cosine x, cosine B, cosine pi halves, the special angle, and figure out what that is. Sine A, A is x, sine x, sine B, B is still pi halves, B is sine of pi halves. Can you figure out the sine and cosine of pi halves? Sure you can. It's an angle coterminal with one of the axes. Quadrantal angle, I think they call those. I draw a pi halves angle in standard position. The point on the unit circle on the terminal side, you're thinking along the y-axis here, is 0, 1. From which the cosine is 0 and the sine is 1. So I pause the video and think about it if necessary, but those claims are true. And we're just left with a sine of x like we were supposed to. So we just turn the left-hand side of this alleged identity into the right-hand side using a summation formula. That proves that. And I bring this up, even though that was not very complicated, to push the following. Did you ever wonder why cosine is called cosine and not something else? Or for that matter, cotangent and cosecant? Where do these cos come from? Here's where they came from, and this illustrates that. X and x minus pi halves are complementary angles. That is, you add them together, you get a 90-degree angle, if you're used to thinking that way. Pi halves radians angle. So angles are complementary if their sum is 90 degrees. Pi has radians. So these two angles are that. They're complementary. So this exercise shows that the sine of an angle equals the cosine of its complement. The sine of this angle equals the cosine of its complement. And the co and complement, that's where the co and cosine comes from. That's why cosine is called cosine. It is related to the sine function through this type of equality when dealing with complementary angles. So the co and cosine comes from the co and complementary. And similar things hold for tangent, cotangent, and secant, cosecant, as you could establish because you got all these damn summation formulas for sines and cosines and tangents, and indirectly secants and cosecants that we stated before. But worth our little bit of time. That's why the words are what they are. It's related to complements of angles, and it didn't take much time to do so. All right, who's next? Law of cosines. Recall the law of cosine states, and I cover this because it's in section 1.3. We may use the law of cosines in passing. If so, I suspect we'll have to recall it because we're not going to use it enough to remember it. Law of cosine says, if A, B, and C are the lengths of sides of a triangle, ABC, with the opposite angles, correspondingly, angle C is opposite side C, then C squared equals A squared plus B squared minus 2AB cosine angle C. So the C squared is on this side and the angle C is on that side. You've seen the law of cosines before. Just make a super quick observation. This part reminds me of the Pythagorean theorem. Hey, what if angle C is a right angle? Then what's a cosine of pi has? We just were talking about that. It was 0. So if C is a right angle, cosine of 90 degrees, cosine of pi has is 0. This part disappears if C is a right angle. Also, if C is a right angle, then this side C is the hypotenuse. And we get hypotenuse squared equals the sum of the squares of the other two sides because that's 0 when capital C is a right angle. So this is really a generalization of the Pythagorean theorem. You want to see a proof of it, go to town. There's one in my pre-calculus notes posted online. We got other fish to fry. Law of sines says if A, B, and C are sides of a triangle, capital A, capital B, capital C, with angle A opposite side A, and similarly for B and C, then sine A divided by A is the same as sine B divided by B is the same, as sine angle C divided by side C. Law of sines, it implies that the ratios of the sines of angles is the same as the ratios of the lengths of the sides in any triangle. Law of sines and cosines hold not in right triangles, but in any triangles. There was no hypotheses about right triangles. Law of sines, I'll be surprised if we use that. I'll be a little surprised if we use that. I think we'll touch on the law of cosine somewhere along the line. We'll recall it if we need it because we're not going to use it that much. Proof of the law of sines, see pre-calculus 2. So yeah, these really play a big role in the pre-calculus trig stuff. And they play roles in applications, and we may see them in those roles. One comment about graphing. The book defines the general sine function as follows. They could just as well talk about a general cosine function or a general tangent function or the other 3 trig functions. So they've chosen to illustrate these ideas, and this is where the phase shift stuff will come in, though they won't use that terminology in this book, it looks like. General sine function is a function of the form f of x equals a sine 2 pi over b parentheses x minus c, close off the big parentheses, plus d. So we got a sine function, we got an x, and we got a bunch of numbers. In this form, the amplitude of that sine function is the absolute value of this number. The period of that function is the absolute value of this number. The horizontal shift is this number. That's related to the phase shift, if you've seen phase shift before. And the vertical shift is this number. In section 1.2, there's information about these horizontal and vertical shifts. We could also think of the amplitude as a vertical stretching of the function in a sense as well. And what we get if we graph this general sine function is the following. Really, instead of memorizing all these letters, the easiest way to think about it is, hey, when does that sine function get fed 0? When does it think it's starting? Because I know what a sine function looks like. It starts here and it waves like that, and then it repeats that. Well, when does that function think it's starting? When is that highlighted stuff 0 for what value of x? When x is c. When x equals c, that general sine function thinks it's starting. So if we'll go over here to x equals c, and they haven't labeled the x-axis down here. Let me get a touch smaller. They haven't labeled the x-axis, but they have indicated that we shifted over c units here, assuming c is positive in the picture. So when x equals this c value, that function sees an input of 0. This 2 pi over b times quantity x minus c, that's 0 when x equals capital C. All right, so the function kind of, I word it like this, it thinks it's starting when x equals c. So that wave, that sine wave, will start here. This offer also valid for the start of cosine waves, tangent waves, and the others. So it thinks it starts here. That's the horizontal shift stuff. The amplitude tells how high up that function goes and how far down it goes. So the amplitude is reflected by this displacement from the average. The average, sometimes called the axis of the trig function, is what's been added on over here. So we get a vertical shift by amount d. In the picture, d is positive. If d were negative, we'd shift it downward. So we get y equals d is the axis, if you like, of that sine function. And it goes a units above there and a units below there, reflected by the amplitude. The period is the absolute value of b. So I said it starts here. Well, b units later, it'll be done. It'll finish over here. The distance from here to here is b units. I wish they hadn't drawn it like this. They've covered b units and they say this is the period of the function, but I really like to think it started here, it went through one period and it ended here. And I say the distance from here to here is b, that's one period. I can't argue with what they did, but I wish they would have started measuring here at the horizontal shift, x equals c. So that's what we get if we're given a sine function with some numbers in it. We put it in this form and graph it based on that information. Speaking of, let's see, we'll do one. I've got that last. Let's jump ahead and do that next. All right, let's do that now. There's one other thing I want to touch on. We'll come back to it. They state the general sine curve formula, and they give you a function. They say for y equals 1/2 sine pi x minus pi plus a half, identify a, b, c, and d, and sketch it. Okay, first off, that ain't exactly in this form. It looks like a is 1/2, d is 1/2, and the stuff inside the sine function doesn't look like this formula. So we got to make it look like that formula. Okay. Let's take the pi x minus pi inside that sine function and factor the pi out. That leaves us with pi times x minus 1. Which is closer. We still need a 2 in front of the pi. All right, we'll put a 2 in front of the pi. To keep the books balanced, you got to divide by 2 at the same time. So we'll multiply by 2 over 2, if you like. So we really haven't changed anything. We multiply by 1. That don't change things. And this is in that form, exactly. We got the 2 pi out front. This must be b, and this must be c. So comparing corresponding pieces, so we did the manipulations to make it look like this. A must be 1/2. the thing in front of the sine function. We got the 2 pi where it's supposed to be. Under the 2 pi is b. B must be 2. B equals 2. We're subtracting off something inside. We're subtracting off 1. So C must be 1, positive 1. Notice there's negative signs in both of them, so we're good. C is positive 1. D is what's added on the right, and 1/2 is added on to the right, so D must be 1/2. Okay, so that gives us amplitude, period, horizontal shift, and the axis as follows. And I've color-coded all of them. All right, let's maybe start with the D. D is 1/2, that'll be the axis, so it'll oscillate around this horizontal line, y equals 1/2, y equals D equals 1/2. The amplitude is 1/2, so it'll go 1/2 a unit up and 1/2 a unit down. So I've indicated that with this a little colorblind problem myself. I'm gonna call that purple. I think it's purple. The little purple arrows indicate the 1/2 a unit up and the 1/2 a unit down. Oh, and that's happening because of this purple 1/2 right here. C equals 1. So we'll shift the sine wave over 1 unit in green. So a green C value here moves it over 1 unit. And this is where I say that sine function thinks it's starting right here at this red dot. So it thinks it's starting there. When I plug in x equals 1, that sine function, so I left the sine part off, that sine function sees 0. And it thinks it's starting, and a sine function starts in the center of a wave and goes up. So it thinks it starts there. And what was the period? The period is B, this thing here in orange is 2. So 2 units later, it'll finish. So I put a red dot at the beginning and the end. The period's 2. I labeled it. This was what I was complaining about in their picture. Labeled it as these 2 units here. So it starts here. It goes up, amplitude 1/2 units. Goes down, amplitude's 1/2 units. And it finishes a single wave in a period of 2 units, from 1 to 3. So that reflects D, the translation upward, C, the translation to the right, like a phase shift, and the amplitude A in the period B. So that picture contains all the stuff we know about that function. So it looks like that. All right, one last little observation, whoops, not there, to the notes. And that's an example from the books. Let's back up in the supplement and catch this. Claim is, for any angle theta measured in radians, we have the following relationship. The sine of theta is between the absolute value of theta and negative absolute value of theta. 1 minus cosine theta is between absolute value of theta and negative absolute value of theta. Why you would want to establish these things? Well, if you got a little bit of experience in calculus, sine theta, 1 minus cosine theta, some limit values we'll deal with, these might ring a bell. So we're going to use these when we do some limit stuff with trig functions. And we're going to do limit stuff with trig functions in chapter 2. So anyhow, let's establish this by going to the supplement. I need to go backwards a little bit till we get to the statement of it. There we go. Okay. So let's establish that, and we'll do it with a picture. So consider this circle. We've drawn an angle, theta, in standard position. We've drawn an acute angle, but the argument will hold for an angle which is positive, negative, acute, obtuse, or anything, because we're going to put some absolute values on some of the stuff. All right. In this picture, figure 1.47, we put theta in standard position. We've drawn a unit circle. How can you tell? Because this point over here is the point 1, 0. Okay, so that's a unit circle. We want to look at the absolute value of theta. Absolute value of theta would equal the length of the arc from A to P. We defined, for positive thetas, we defined the radian measure of theta to be that distance there. When theta was negative, we throw a negative sign in. When I can have angles have negative measure, but I can't have distances be negative. So that's where the absolute value really comes from. So we've got the absolute value of theta is the arc length from A to P. That's how you measure angles in radians. Okay, this same figure, we want to compare the length of segment, line segment, AP, so straight line shot from A to P, compare that to the arc length. Well, we see from the figures, depending on the picture a lot, we see that the distance from A to P is less than, or maybe less than or equal to, just to be on the safe side, the arc length from A to P. And the arc length from A to P, we just said, was the absolute value of theta. So this little orange line segment of length AP is less than or equal to the absolute value of the angle theta, measured in radians, which is the distance along the crust of the pie there, as I've described it, the distance along the circle of that circular segment from A to P. We've got a right triangle. Triangle APQ is a right triangle. APQ, yeah, so there's a little right triangle. There's another one there in blue, but we're talking about this one now. APQ is a right triangle. The sides are lengths. Absolute value of sine theta. Yeah, sine theta, that could well be negative. Like I said, theta could be any angle. So this could be a picture where we've actually got a terminal side down here in the fourth quadrant. The conversation still works. I'd have to modify the picture. And I'd need absolute values on this y coordinate of point P is what we technically have. So I need absolute values on the sine theta if I'm going to talk about distances. So yeah, geez, we got negative values for the trig function. So I can't use them directly to measure distances, but I can with absolute values. So we've got a right triangle. This length of this side will be absolute value of sine theta. The length of this side will be 1 minus cosine theta, AQ, distance 1 here. Cosine theta is what we get out in terms of this distance, or I guess that could be negative as well. We're going to need absolute values on this. 1 minus cosine theta. Could that be negative? No, we're good. Remember, cosine is between -1 and 1. Okay, so then 1 minus cosine, the least this could be is 0, and the most it could be is when cosine is -1, it'd be 2. It's between 0 and 2. So I don't need absolute values on this part. So right triangle, absolute value of sine theta here, and 1 minus cosine theta here. No absolute values necessary. Okay. Well, that gives us, by the Pythagorean theorem applied to right triangle APQ, gives us sine squared, or absolute value of sine squared. Yeah, squared it, so I don't need the absolute value. So I know this is non-negative, whether I put absolute value on it or not. So we're doing that little thing. 1 minus cosine theta squared equals hypotenuse squared. Hypotenuse in that little triangle is this orange straight line segment. That's segment AP, represent its distance by AP as well. And so we get sine squared theta plus 1 minus cosine theta squared equals hypotenuse squared, equals AP squared. Oh yeah, and we were saying that straight line distance is less than the length of that circular arc, which had length absolute value of theta. All right, so if AP is less than the absolute value of theta, then AP squared is less than or equal to absolute value of theta squared. Oh yeah, I square it, I don't need the absolute values. So we've established this inequality from that figure. All right, so we've got sine squared plus something is less than or equal to theta squared. That's something, that's non-negative because it's something squared. So we've got sine squared plus something, non-negative, is less than or equal to theta squared. Well, then sine squared itself is less than or equal to theta squared. Sine squared itself is less than or equal to theta squared. And similarly, we've got 1 minus cosine theta quantity squared plus a little something non-negative is less than or equal to theta squared. Well, I can drop that little non-negative thing and draw the conclusion then that this squared is less than or equal to theta squared also. If either of these plus a little something positive is less than theta squared, then one of these individually is even more less than theta squared. Weak, little informal there, but that's the idea. All right, so we've established this and this from the figure. Let's take square roots because we made a claim about sine theta, not sine squared theta. So we'll take square roots. Okay, we're taking square roots of something squared. Ooh, that's when you have to introduce the absolute values. So we'll take the square root of both sides. Square root function's an increasing function on non-negative inputs. We've got non-negative inputs. So the inequalities are preserved. Square root of sine squared is less than square root of theta squared. What is the square root of sine squared? Take a square root of something squared. That's the absolute value of the something. So we get absolute value of sine theta, and on the other side, we get absolute value of theta as well. So we actually get these absolute values introduced. That was the definition, or an alternate definition, of the absolute value function. Square root of something squared is not the something, it's the absolute value of the something. So you're stuck with those absolute values for now, at least. And similarly, when we take the square roots of both sides of this inequality, we get an absolute value of 1 minus cosine theta is less than or equal to the absolute value of theta. Okay, now we need to rewrite this by getting rid of the absolute value on the sine theta and on the 1 minus cosine theta. To do so, Appendix A1 tells you how to deal with inequalities involving absolute values. To do so, I take the sine theta absolute value of, drop the absolute values, keep the upper bound as absolute value of theta, and take the negative of that as a lower bound. See section A1 if you don't like the sound of that. It's discussed in not great detail, but it's mentioned in Appendix A1. So that's how you remove an absolute value on this center term. And similarly, 1 minus cosine theta, drop the absolute values, keep the upper bound of absolute value of theta, and put a lower bound on it of negative upper bound, negative absolute value of theta. And those two things were exactly what we claim. Why you would want to know this, sit tight. We'll explore it in chapter 2, but that gives us an inequality related to sines and cosines that we'll use later, and it'll be a big deal in chapter 2. So that takes care of 1.3 trig functions. 1.4 is about some using software. We're going to skip that one. And next section we'll do is 1.5, and that's on, if memory serves, exponential functions. It's not quite as long as this section 2. So have a nice day. I hope to see you soon, figuratively, in section 1.5. Have a nice day.